We've measured basically when we've actually looked at one coordinate system alone, and we've dwelt a lot on what? Cartesian coordinate system. But when you're dealing with electromagnetic field theory, there are other two coordinate systems that we normally use. So it's necessary that we look at our coordinate system that is used in electromagnetic field theory. So, electromagnetic field theory, we have three coordinate systems. We've said Cartesian, which is common from even your vector analysis in second year. We have Cartesian coordinate. So again, we have cylindrical coordinates. Then thirdly, we have spherical coordinates. Now that all of us are in touch, or we know the Cartesian coordinate system, I'm going to focus basically on cylindrical and spherical coordinate system. So let us start with cylindrical coordinate system. So, cylindrical coordinate. So say a point P in cylindrical coordinate, P in cylindrical so a point P in cylindrical coordinate is represented as, now this is not P but rho, comma, phi and z. So rho, phi and z as shown below. As shown below. So now we want to have our coordinates. So we are using the right hand rule method. So this is our z-axis, this is our y-axis, and this is our x-axis. So we want to draw a cylinder so that we represent our cylindrical coordinate system. So we want to represent point P in that cylindrical coordinate system. Now that movement of angle from x-axis to the point on the cylinder, point P on the cylinder, is what we are calling as phi. Then we have the radius of the cylinder from this, the center point, which is still the same as that to that, is our rho. This is our point P. So this is point P. So we have rho, phi. Just a minute, let me just indicate it here. This is my point P. Then the height of that cylinder is Z. Now we have unit vectors of this particular point P. Now the unit vector along the radius of the cylinder is indicated as, it is a rho. That is the unit vector in that particular direction. And the unit vector that goes along the z-axis or parallel to the z-axis, we'll indicate that as AZ with a bar on top. Similarly, the unit vector that is tangential to the curve, this, now that will be our unit vector A phi with a bar on top. Now that is how we'll represent a point P in a cylindrical coordinate system. Now we can maybe say, so define what these values are. Rho, phi, and z. So we can say here that where rho is the radius of the cylinder, it is the radius of the cylinder. Then next term is phi. The order should be the same always. We start with rho, phi, then z. So then phi, that is the azimuthal. It is the azimuthal angle measured. It is the azimuthal angle measured from the x-axis. Then we also have z. So z is the same as in Cartesian. It is the same as in Cartesian coordinates. Now, when we are also again dealing with this cylindrical coordinate system, again, it's also very necessary that we know the range, the ranges of values of rho, phi, and z. So we can say the range or the ranges of the variables. The ranges of the variables are, now if we look at rho starts from the center going onwards. You see the cylinder can be so big, so we can say that rho will range from 0 to the value of rho goes up to what? Infinite. Similarly, the angle now, since it is a cylinder and the whole of that circumference makes an angle of 360 degrees, then we can again say that the range of phi will range from 0 to the value of phi being the same as 2 pi or 360 degrees. 2 pi is in radians, which is equal to 360 degrees. And similarly now, the xy plane can be somewhere at the center so that we can have positive values of z and negative values of z. So z also can go infinite. So we can similarly say that the ranges of z will range from negative infinity to the value of z being equals to what? Infinity. These are the ranges that we use, and it's very important to take note of, especially the ranges of phi. This one tends to confuse most of the students when they are trying to substitute, especially where we'll be dealing with the integration of vectors. So those are the ranges of these variables. So just like in Cartesian coordinate system, we can also represent a vector in cylindrical coordinate system. So maybe we can say that a vector A bar in cylindrical coordinates is represented as, so you can say our A bar will be the same as, because we say the first term is rho in the direction of a rho, plus the next term becomes a phi in the direction of a phi, plus the next term is az in the direction of az. So that if we have a unit vector of this, then it's the same way we are dealing with it. If that be the what? If we have this as our vector, then what will be the magnitude will be the same as that. As our magnitude, it should be the root of a rho squared a phi squared plus a z squared. So that is that. Again, if we apply the rules of dot and cross product rules to be followed, still the same. Our rules will be a rho dot a rho will be the same as a phi bar dot a phi bar, which is the same as a z bar dot a z bar, and that is equal to 1. And a rho dot a phi is the same as a phi dot a z, which is the same as, this is supposed to be an equal sign, which is the same as a z dot a rho, and that is what? 0. And if we do our cross, we are saying that our cross product rule to be followed so we are saying that this will be a rho cross a phi, then we have a phi cross a z, then we also have a z cross a rho, and this, so this will give us a z, and this will give us a rho, this will give us what? A phi. We can still do a cyclic permutation method, and we will have a rho a phi, then you also have a z, so that we have that. So a rho a phi will be a z, a phi a z we have a rho, a z a that we have the one exactly opposite, which is what? A phi. So that is how we represent what? These are the two rules to be followed when applying what? Dot and cross product for cylindrical coordinate system. Now, how do we relate cylindrical coordinate system with Cartesian coordinate system? Now, from the figure below, from the figure that we are about to draw, we can easily see how cylindrical and Cartesian coordinate systems are related. So we can say the relationship, between variables x, y, z of Cartesian coordinates and those of cylindrical coordinate system and in cylindrical we said it is rho, phi and z are obtained are obtained from the figure below. So let us see our simple figure that will relate the two coordinate system, and it's also very important. So if we have that as our axis, our z axis, then we have this as our y axis, and then we have that as our x axis, like so. So let's say that this is a point somewhere in space. Let's draw some point, yeah, like so. This is parallel to that, this is parallel to this. So we have that, and this is x. Then the angle that makes with that, we are calling that as what? Phi still. This is my radius of the cylinder, like before, it is rho. So this is x, which is the same x there. We have y, we have that. So we can talk of a height from that point upwards, which should be parallel slightly. Just a minute. Like so. Yeah, this is the point that we want to relate. It's still point P. So P has coordinate of x, y, and z, which is still point P. We have coordinates of rho, phi, and z. So we are interested in that particular point. We are calling as point P. Now we have some triangles there that we've drawn, and those triangles we want to relate them so that we can get a representation of x in terms of cylindrical coordinates. Similarly, a representation of y, which is y here, in terms of cylindrical coordinate system. Now, how do we go about that? Now, this is a right angle triangle. That is the angle 90. Yeah, if we draw that upright, like so, we've rotated it such that this is my x-axis. Yeah, we have x there, and x makes an angle with the hypotenuse, and that angle is what we are calling as our phi. So x is making an angle, the length from here to here, the hypotenuse is indicated as rho. So we have x, and the opposite is y. Now, if we apply our trigonometry a bit, so if we are to get the cosine of that angle phi, cosine of phi is going to give me what? So if we look at our SOHCAHTOA, because that is what we want to apply, so the cosine of y will definitely give me the adjacent, which is x, over the hypotenuse, which is what? Rho. So this implies that x must definitely be what? Rho, the cosine of phi. So this length here must be rho, the cosine of phi. Similarly, if we look at the sine of the angle phi, we are saying that our sine must be what? Y, or which is the opposite over the hypotenuse, and still our hypotenuse is rho. That similarly implies that our y must be rho, the sine of phi. So this y of ours will definitely be rho, the sine of phi. So we've actually got that, and rho itself, since it's a right angle triangle, then we can use our Pythagoras Theorem and get the value of rho, so that rho will be the square root of the square of the adjacent added to the square of the what? The opposite side. So that is what we get. So if we are to represent those values, we have that, and that. Z is the same z. So then we can say that from there, from what we have in cylindrical, yeah, we have that. So again, in if you are to get the angle, sorry, the angle phi can equally be represented by what? Torr from our soccer torr, and torr will be the opposite, the tan inverse of the opposite, which is y, over the what? The adjacent, which is what? X. Now we can comfortably write our relationship that we are talking about. So we can say that in cylindrical coordinates, we start with rho, and we've seen that rho here is represented as the root of x squared plus y squared. Then the next term, which is phi, is represented in Cartesian as being the tan inverse of y over x. Then the last term, which is z, is still the same z in also what? Cartesian coordinate system. So similarly, we can represent it in terms of x, y, and z. So we also found that our x was the same as rho, the cosine of phi. Y was equally the same as rho, the sine of phi, and z is still the same as the other z. So this is the relationship that we find, between Cartesian and what? Cylindrical coordinate system. Now, apart from Cartesian and cylindrical coordinate system, we also have the what? The spherical coordinate system. So just like the way we've analyzed cylindrical, we can also look at the what? The spherical coordinate system. So still again we are saying that a point P in spherical coordinate system, P in spherical coordinate system is represented by the coordinates. A point P in spherical coordinate system, in spherical coordinate system is represented as, now here we normally use r, we have theta and then phi. So phi is the same phi as the one that we have seen in cylindrical coordinate system, is represented as r theta phi as shown below. As shown below. So now we also want to draw our half sphere or hemisphere and then see. So still this is z. That is y. That is still x. So this is the point P. The angle that that point makes with the z-axis is what you're having as theta. Yeah, so that is what we have as P, point P. That now this radius is what you are calling as r. Now that unit vector, again in this particular direction, is known as AR. Now unit vector that is tangential to this, that is known as A theta, because theta is the direction. Now theta is what is creating this curve. So this is A theta, and the one that is tangential to the same curve, this curve again, this now in that particular direction, we call that as A phi. So that is what we have as our point P. Now similarly, the same way that we've looked at the other system, also in spherical system we have the rules that we are supposed to follow. So we have that before that, maybe we can say maybe those variables or the range of R, theta, and phi R. So the range of R, theta, and phi. Now if you look at R again, R just like the radius of the cylinder, it's also starting from the center, which is 0 point, and going all the way, all along. So this sphere can be a very big sphere like the Earth. The Earth is a sphere. Yeah? So we are saying that this can go up to that big range. So that range we can say that it can be from 0 to R all the way to infinity. See, the Earth's surface is around 64,000 kilometers. So that is also a very big range. Then again, theta, because it's a half sphere, we are saying that theta goes half of it, not the whole sphere. So theta is a half of 360. So we can say that this also will range from 0 to theta being equals to what? Just pi. So similarly, phi is the same phi as the other one, and you are saying that that phi will range from 0 up to phi being the same as equals to 360, which is the same as what? 2 pi. Yeah? So those are our ranges of that. So still again we can say a vector A bar in spherical coordinate, a vector A bar in spherical coordinate is represented as, so we are saying that A bar will be AR of AR bar plus A theta of A theta bar plus A phi of A phi bar. So this is our vector. So definitely the magnitude of that vector must be the same as the root of AR squared plus A theta squared plus A phi squared. So that is how we will represent our magnitude. So equally you can get our unit vectors for this, for this vector in spherical coordinate system. So still, we also have our rules, which we are saying that the dot and cross product rules to be followed again here. They don't change, they're just the same. Once you have similar unit vectors, you'll get a 1 because the angle between them, or the cosine of the angle between them, is 0. So the cos of 0 is 1. So we are saying that AR dot AR is equals to A theta bar dot A theta bar, which is the same as A phi bar dot A phi bar, and that is 1. If you get the opposite of AR dot A theta, must be the same as A theta dot A phi, which is A phi dot AR, and that is 0. Still, if we do a cross product rule, we can say that AR cross A theta is equals to A phi. A theta cross A phi is the same as AR. A phi cross AR will be the same as A theta. You can still also apply the cyclic permutation method for the two. So now we want to again to look at the relationship. The relationship involves relationship between Cartesian, cylindrical, and spherical coordinates. So now let us see the relationship between the three. So we have a figure here. Like so. So still we have Z, we have Y, we have X. So we want to draw that. So this is y-axis, z-axis, that. Still this is our angle. That angle is phi, as usual. Now this is the radius of the cylinder. See, we are relating all of them, and that is rho. Now from this point all the way to that. Now this is my point P that we are interested in. P in x, y, z coordinates, which is still P in r, theta, phi coordinates, which is still P in rho, phi, and z coordinates. So we have that as being rho. This should be the radius now of the sphere. Then this is the angle that the sphere makes with that point. We are also calling that as our theta. Now we want to draw right angles triangle here. Now again, just the same. We had said initially that this was 90 degrees. Similarly here, this also makes a what? A 90 degrees. So I have two right angle triangles that I want to relate. If that is x, so this from here to there is x, which is the same as that x. This is y up to this point, which is the same as up to that point. Let us call that as y. So we need to find the value of y, which is that, and we need to find the value of rho. This is rho, and is the same as that rho. This is z, and that side is also z. So that is what we want to relate. So I need to draw the two right angle triangle once more and see our relationship. Though we had drawn the first one, we had that, this angle that it makes, this is rho, which is our hypotenuse. This is phi. The adjacent is x, the opposite is y. And I also have this other one. Still have to draw it like a right, not like, but it is a right angle triangle, like so. So the hypotenuse is r, the angle that it makes with r is theta, and the opposite of theta is rho. So those are the two right angle triangles that we have, and we want to see how we can get the relationship in them. Now, if you look at it keenly, from what we have there, we are saying that we had initially developed this for the first right angle triangle, and we found that x was the same as rho, the cosine of phi. Similarly, we found y to be the same as rho, the sine of phi. And we also knew that z is the same as z in that coordinate system. And we went further and found that relationship in Cartesian. And in Cartesian, again, we found that rho was the same as the square root of x squared plus y squared, and phi was the same as the tan inverse of y over x. Still, z remains as z. Our interest in this is in this other right angle triangle, that one there. So if we relate that, if we start with r from this, our adjacent is that z. I didn't indicate this, it's still there, z, and so we have that z. So if we are supposed to get r, so r must be the root of the square root of that. We are using our Pythagoras Theorem here, and this will be rho squared plus z squared. That is our r, yeah? Then again, apart from, we say that it is r theta, then phi, and our theta will be what? From the same, theta must be the tan inverse of the opposite, which is rho, over the adjacent, which is z. So, and phi will be the same as the other phi in what? In cylindrical coordinate system, and that phi is the same as tan inverse of y over x. Now, from what we have up here, maybe I can call this as 1, this is 2. Now, if you look at our equation 2, because 2 carries a lot of them here. If we look at 2, rho can still be defined in Cartesian coordinate system as x squared plus y squared square root. So, but rho square is just x squared plus y squared. So, I can equally write r as being the root of x squared plus y squared plus now z squared, where this represents rho. X squared plus y squared is rho. So we have z, which is that. Similarly, I can still write theta as being the tan inverse instead of rho. And rho is that, will be the root of what? X squared plus y squared over z. So still we have phi here as being what? Tan inverse of y over x. So that is how we relate the spherical, cylindrical, and Cartesian coordinates using this diagram of ours here. So next time, we'll look at more example on what we've covered, and in our next vector analysis subject, we are going to look at the integral or the calculus part of vector analysis. Basically, we are through with our coordinate system. So the next lesson, basically, we look at the differential form. Yeah, form of length, surface, and volume. We'll also dwell on the vector calculus. And on vector calculus, we need to know the divergence theorem and Stokes theorem.